Hello everybody, thank you for joining me and welcome to my presentation. Before we begin, let me introduce myself briefly. I'm Levke Wiehler and I'm currently working as a soldier and a research associate at the University of the Bundeswehr in Munich at the Institute for Material Science. The investigations of the present study concentrate on the crack detection and localization with multiple potential drop measurements. Let me start off with the introduction into the direct current potential drop method, short DCPD, which is commonly used to measure the crack length in fatigue tests. Therefore, a DC source conducted a time-stable current through the specimen during the test. The measured voltage U represents the difference between two potentials. On the right side, the relative potential difference is plotted over the cycle number. As soon as the crack grows, as seen on the specimen, the measured potential difference increases until the failure of the sample. Due to a propagating crack, the cross-section of the specimen is reduced, leading to a densification of potential field lines. To give you a brief overview of where we are in the presentation, a short outline follows. First, a description of the test procedures, followed by the results. Those are divided into the determination of the time and location of cracks and the determination of the shape of the crack front. Finally, a short conclusion. Fatigue tests were carried out using a servo-hydraulic testing machine equipped with a Dolly EDC 580 control electronics with the following baseload. In this study, single-edge notched specimens were equipped with 3 potential probes, on the front side, on the back side, and on the narrow side of the specimen. Secondary notches were lasered in the notch root to force crack initiation at a defined position. To enable a direct comparison between the potential drop measurement and the real crack geometry, the crack front was marked on the fracture surface by introducing overloads at defined intervals. For the potential drop measurement, copper wires with a diameter of 0.2 mm were laser welded to the specimen. The distance between the two contact points of a potential probe was 3 mm. The measured potential is significantly influenced by the position of the potential grips. I will now follow up with the determination of the time and location of cracks. Because the tests differ, for example, due to the quality and the exact location of the welding spot, the absolute measurement results vary and are therefore not comparable with one another. To remedy this, the measurement results were standardized by dividing the potential difference Ui by the initial voltage Ui0, defined as the mean value of the potential of 200 cycles at the beginning of the experiment. On the right side you can see the run of the relative potentials. What is striking about the run is the decrease of all potentials within the first 20,000 cycles. As I explained earlier, the potentials should rise as soon as a crack is initiated. Because of the decrease, we are not able to detect a crack by only looking at the run of the relative potentials. By the way, this drop is explained with a decrease of the temperature after the beginning of the test. To determine the time and location of crack initiation, the quotient Q is formed by dividing the individual potentials P front and P back by the relative potential of the narrow side P narrow, the potential in the center of the specimen's width. The run of the quotients is visualized in a graph to determine the point in time and location of the crack initiation. To be able to make a precise statement about the time and location of the crack initiation, the first 30,000 to 60,000 cycles are examined in detail. At the beginning of the experiment, both quotients have the value 1. A crack is expected as soon as an imbalance between the quotient Q front and the quotient Q back occurs, or a significant decrease or increase in both quotients becomes apparent. Using the potential quotients, a tendency of the initial crack to the front or back side of the specimen is quickly apparent without neglecting the potential difference of the narrow side. There are 3 possible cases for crack initiation, with each case also applying to the opposite quotient. Let us take a look at the first case. If Q front increases while Q back decreases or remains constant, a crack is initiated near the front side of the specimen. Remember, each case also applies to the opposite quotient. Case B, if both quotients drop, a crack is initiated in the center of the notch. Because the potential on the narrow side of the specimen increases and forms the denominator of the two quotients, both quotients decrease. And the last case, if both quotients rise, cracks are initiated on both sides of the specimen. These criteria can be used to describe the first crack as well as subsequent cracks. In the following, I will present to you those cases on different samples. In sample 1, both quotients initially remain constant until the first overload after 15,000 cycles. At that point, the quotient Q back increases while the quotient Q front decreases. According to the categorization, the first crack is expected near the back of the specimen. The fracture surface of specimen 1 shows a fatigue cracks emanating near the back side of the specimen. By counting back the overload marks, the crack initiation can be assigned to the first overload. Therefore, the detection and localization of the crack was after 15,000 cycles. In case of specimen 2, a crack can be recognized after 11,250 cycles. At this point, both quotients are decreasing and below the value 1. In this case, the potential P narrow exceeds the other two potentials, indicating the initiation of a crack in the center of the notch. Indeed, the starting point of the first crack is in the center of the specimen's width. A second crack becomes visible close to the backside of the specimen. After 15,000 cycles, the decrease of Q front is steeper compared to Q back, indicating the initiation of a secondary crack near the backside of the specimen. The overloads not only frame the center crack but also the secondary crack. This confirms the statement that an initial crack occurred at about 11,250 cycles and a secondary crack between 15,000 and 30,000 cycles. In sample 3, both quotients rise and exceed the value 1 after only 1,800 cycles. According to the categorization, 2 cracks are initiated near the front and backside of the sample. The fracture surface of specimen 3 confirms 2 cracks near both sides of the specimen. By counting back the overload marks, the crack initiation was before the first overload. Therefore, a crack initiation at 1,800 cycles is quite possible. Besides the determination of time and location of crack initiation, reliable statements about the shape of the crack front can be made by analyzing the quotients. In this diagram, not the run of the quotients is shown, but only one cycle. In case of a straight crack front running parallel to the notch, as seen in example 1, all relative potentials, including the potential on the narrow side of the specimen, are equal. Therefore, the quotients Q front and Q back are both 1. When the crack front is inclined, like example 2, both quotients are different, and Q front is greater than 1, whereas Q back is less than 1. Those values are comparable with the crack front itself. The value Q is 1 represents the intersection of the center of the specimen's width with the crack front, depending on the respective overload, and can be visualized as a vertical straight line. Because the potential on the narrow side forms the denominator of the quotient, you can always visualize the relations between all potentials. If this line represents Q as 1, Q front is greater than 1, whereas Q back is less than 1. When the crack front is curved and has the same length on both sides of the specimen, both quotients are equal but less than 1. The crack front of specimen 2 will be analyzed using this method. On the left, the fracture surface of specimen 2 is shown. On the right side, the values of the quotients at the time of the overload are visualized. First, the overloads are marked. To be able to draw comparisons between the fracture surface and the run of the quotients, the overloads are numbered. Afterwards, a line in the center of the specimen's width is drawn in to point out the intersection between the crack front and the value Q equals 1, which can be shown as a vertical line. For simplification, only continuous crack fronts are analyzed which became visible on the fracture surface after the third overload. The diagram clearly shows that at the third overload both quotients are below the value 1, while Q back is greater than Q front. This results in an arced crack front. Looking at the crack front of the third overload on the fracture surface, this relation can be confirmed. Q front is less than Q back is less than 1. If the fourth overload is analyzed, it is noticeable that the quotient Q back has visibly approached the value 1. The quotient Q front has decreased. In addition, the distance between Q front and 1 has increased compared to the previous overload. The slightly convex crack front remains. Therefore, the third to fourth overload are both curved crack fronts. At the fifth overload, the quotient Q back clearly exceeds the value 1, while the quotient Q front continues to represent the lowest point, both in the diagram and on the crack front in relation to 1. Simply put, this results in an almost linear crack front. If the fracture surface is looked at, the crack front of the 5th to 7th overload have almost identical shapes. According to the model described above, the ratio of the quotients to one another should only change moderately, and Q front should remain below 1. In the diagram, however, a steep increase in both quotients can be observed, while both quotients are getting closer. This behavior is probably caused by a distortion of the relative potential difference on the narrow side, or by a lack of calibration of the two lateral potential differences. The investigations have shown that the multiple potential drop measurement enables the early detection of cracks combined with a determination of the crack's location. In the case of single-edge notched specimens, the detection of the crack location can be determined by simply forming the quotient between the relative potential measured on the front, back side and on the narrow side of the specimen. And due to the formation of quotients, potential changes caused by temperature fluctuations are eliminated. Therefore, multiple potentials improve the accuracy of the potential measurement. In this study, a detection of crack initiation was possible at only 1,800 cycles. A detection of crack initiation in a running test is possible by integrating suitable conditions into the control software. From the potential curves, information on the geometry or inclination of the crack front in long cracks can be obtained. A distinction can be made between a straight, linear, or curved crack front. Therefore, invalid results in fracture mechanic tests can be avoided if the shape of the crack front doesn't meet the requirements. In addition, the use for structural health monitoring is also conceivable. In conclusion, the multiple potential drop measurement offers new possibilities for the investigation of crack initiation and propagation in fatigue experiments. Thank you for your attention, and I'll be happy to answer questions.